Hi there. In this session, we are going to walk through a realistic DevOps interview focused on databases, replication, and backups. These are the areas where small decisions can have huge consequences in production. So the goal here is to test your reasoning, not just your memory. I will ask questions, give you space to think, and then walk through a strong sample answer. If you want to get the most value, pause before each answer and try responding out loud. And if you want to follow along with future interviews, make sure to subscribe so you do not miss the next one. Let's begin with a few behavioral questions to understand how you think about reliability, data safety, and operational discipline. Tell me about a time you were responsible for a database outage or near miss. What happened and how did you address it? A strong answer might sound like this. I once applied a schema change that added a new index on a large table during peak hours. The query planner reacted badly, and the database slowed down significantly. Once I realized what was happening, I paused the migration and shifted traffic away from the impacted cluster. Then I ran the indexing job in smaller batches during off-peak hours. Afterward, I updated our deployment guidelines to include safer windows for heavy migrations. The biggest lesson was respecting how expensive certain operations can be and coordinating them with the business. Next question. Tell me about a time when a backup saved you from major data loss. What did you learn from that situation? A solid answer would be: we had a corruption issue after a faulty application release wrote malformed data to a critical table. Because the corruption was subtle, it went unnoticed for several hours. Once we discovered it, we restored from the most recent backup and replayed the bin logs to recover everything up to the minute before the bad writes. That experience taught me the value of point-in-time recovery and regularly testing restore procedures. A backup that is not tested is just a file, not a guarantee. Next, behavioral question. Describe a situation where replication lag caused real problems. How did you detect it, and what did you do? A thoughtful answer could be: we used red replicas for performance. During a traffic spike, one replica lagged behind by several minutes, so users got stale data. Our monitoring alerted us because the replica delay crossed our thresholds. I temporarily removed the lagging replica from the read pool and increased capacity on the primary. After stabilizing traffic, I tuned the replica's settings and hardware to catch up. The key was treating replication lag as a serious reliability issue and not just a performance metric. Next question. Give me an example of when you had to push back against a request that might have put data at risk. A mature answer might be: a team requested direct database access so they could run analytics queries. The queries were heavy and risked impacting the primary. Instead of saying yes, I set up a read-only analytics replica and gave them controlled access. This protected production while still meeting their needs. It taught me how important it is to safeguard the database, even when it means negotiating with other teams. Final warm-up question. Tell me about a time when a backup strategy that seemed correct turned out to be incomplete. A good answer would be: we were backing up the database nightly, but failed to include a separate file storage directory used for user uploads. When we needed to restore, the database came back perfectly, but the files did not. That forced us to rethink our definition of backup. It is not just about the database. It is about the entire data footprint. After that, we implemented unified backups for both database and file storage, plus periodic recovery drills. Let's move into the first half of the technical section. These questions dive into replication, durability, and real-world failure modes. Explain the difference between physical backups and logical backups. When would you choose each? A clear answer might be: physical backups copy the actual database files. They are fast and efficient for large datasets, but less portable. Logical backups dump the data and schema in a human-readable format. They are slower but more flexible. I choose physical backups for high-performance production environments where speed matters, and logical backups when I might need portability, or when migrating between database versions or platforms. Each has different restore characteristics, and the choice depends on recovery time and compatibility needs. Next question. You notice replication lag gradually increasing over time, not from a sudden spike. What are some reasons this might happen? A strong answer would be gradual lag suggests that the replica cannot keep up with the incoming write volume. It might be slower hardware, slow disk performance, or inefficient replication settings. Long-running queries on the replica can also block replication. Another possibility is that writes are becoming larger or more frequent. I start by checking replication threads, slow queries, disk IOPS, and network throughput. The root cause often reveals whether scaling or tuning is needed. Next scenario, your database supports point-in-time recovery. A developer accidentally deleted a production table at 9:42 a.m. Your latest backup is from 2 a.m. Walk me through the steps you would take to restore the data. A thoughtful answer would be, I would spin up a temporary restore from the 2 a.m. backup. Then I would apply the bin logs or WAL files to replay changes forward until just before 9:42 a.m. Once the restored database is at the correct point in time, I extract the missing table and import it into production. I do all of this in isolation so I do not disrupt the live system. The key is precision and verifying that the restored data is consistent before reinserting it. Next question. Explain what could cause a replica to diverge from the primary. A solid answer could sound like, divergence can happen if replication is not strictly synchronous, if there is a network partition, if the replica has been configured incorrectly, or if there is an unhandled conflict. In some systems, temporary write access to the replica can cause it to drift away from the primary. Corrupted replication logs or storage failures can also create divergence. The repair strategy depends on the root cause, but often involves rebuilding the replica from scratch. Next scenario. Your daily backups are successful, but restores take too long. Recovery might take several hours, which is unacceptable for your business. How do you reduce recovery time? A strong answer would be, I look at incremental backups so we do not always restore an entire dataset. I also consider faster storage for the backup archive. Another option is keeping a warm standby system that is continuously replicated and can be promoted quickly. For very large databases, I might partition data or use parallel restore techniques. The goal is reducing recovery time without sacrificing safety. Let's continue with the second half of the technical section. These questions focus on difficult database scenarios, subtle failure modes, and the trade-offs that come with replication and backup strategies. Here is the next scenario. Your primary database is under heavy load, and you decide to offload reads to replicas. After shifting the traffic, users begin reporting inconsistent data. Some pages show old information, while others show the latest. What do? A strong answer would sound like this. Read replicas are eventually consistent, so the first step is confirming the replication lag. If the lag is more than a few seconds, users will naturally see different states depending on which replica they hit. I check the replication metrics, slow queries, disk performance, and network saturation. If the lag is caused by heavy reporting queries on the replicas, I isolate analytical workloads onto dedicated replicas. If the replicas simply cannot keep up with write volume, I consider scaling up the primary, optimizing indexes, or reducing the write workload. In the short term, for user-facing critical paths, I may redirect those specific queries back to the primary to guarantee correctness. The goal is balancing consistency against performance. Next scenario. You are migrating a production database from one major version to another. The new version supports different replication mechanisms and backup formats. How do you plan a safe migration? A thoughtful answer would be, I start by cloning the production data into a staging environment so I can validate compatibility with the new version. I test all schema migrations, stored procedures, and application queries. Then I verify that replication works correctly in both directions if I need a rollback path. I also run controlled load tests to make sure performance characteristics are acceptable. For the actual migration, I schedule a maintenance window, stop writes, take a final backup, perform the version upgrade, validate the data, and only then reopen traffic. If something goes wrong, my rollback plan involves restoring from the final backup and promoting the older version. The entire process must be rehearsed ahead of time. Next question. Your backup system stores daily snapshots in object storage. You discover that the last 3 snapshots are corrupted or incomplete. You do not yet know why. What is your immediate approach? A composed answer might be, I first isolate the problem by checking whether the corruption occurred during creation, transfer, or storage. I verify the integrity of earlier snapshots and test restoring them. I look through the backup logs for signs of interrupted jobs, disk errors, or network failures. At the same time, I immediately enable an emergency backup with a different method if available. That might be a logical dump or a physical snapshot. My priority is ensuring that at least one valid backup exists before investigating deeper. Backup failures are critical risks, so stabilizing the safety net is the first step. Next scenario. Your application writes to a primary database and reads from replicas. Suddenly, the replicas start returning rows that should have been deleted hours ago. The primary shows the correct state. Replicas do not. What does this tell you? A strong answer would be, this almost always indicates replication lag or replication failure. Either the replicas have fallen behind and have not fully processed delete events, or replication is broken entirely. I check the replication threads and logs. If replication is stopped, I restart it and monitor for errors. If it is running but very slow, I inspect long-running queries, disk contention, or poorly indexed tables that slow down the application of delete operations. If the replica is too far out of sync, the safest approach is to rebuild it from the primary. Stale replicas can cause severe correctness issues, so restoring them to a known good state is essential. Next scenario. You need to design a backup and restore strategy for a database that handles both critical financial data and high-volume logs. The financial data must always be perfectly consistent, but the logs can tolerate some loss. How do you design the strategy? A thoughtful answer would sound like this. I separate the 2 classes of data. The financial data must use point-in-time recovery, frequent bin log archiving, and regular full backups. I might also keep a warm standby replica for rapid failover. For the logs, I use cheaper and less frequent backups because their correctness is not mission critical. This reduces cost and storage usage. I also ensure the restore workflow can recover the financial data independently without being blocked by the log data. Designing separate paths for different data categories is the safest and most cost-effective strategy. Final technical question for this section. A sudden spike in write traffic causes your primary database to fall behind on flushing its write-ahead logs to disk. Replication starts lagging badly. The system is still technically working, but you know a crash could result in data loss. What do you do? A strong and realistic answer would be, I reduce write pressure immediately. That might involve rate limiting the incoming traffic or temporarily degrading features that produce high write volume. I check disk performance because saturated disks can slow WAL flushing dramatically. If storage is the bottleneck, I shift the WAL directory to faster storage or provision temporary high-performance disks. I also ensure that synchronous flushing is enabled so durability is preserved. My priority is preventing a crash while restoring healthy write throughput. Once the immediate risk is gone, I can investigate the root cause, whether it is new workload patterns, misconfiguration, or hardware limits. Let's move into the pressure section. These questions are designed to test your judgment when information is incomplete, risks are high, and decisions must be made quickly. Here is the first scenario. Your primary database is showing signs of corruption in one table. Replication is still running, which means the corrupted data is already propagating to the replicas. You are not sure whether the corruption is isolated or widespread. What is your first move? A mature answer would sound like this. I stop replication immediately. If corruption is spreading, I want to contain it before it affects every replica. Once replication is paused, I isolate the affected table and check its indexes and storage files. I verify whether backups from earlier in the day are healthy. After confirming the blast radius, I decide whether I can surgically repair the table or need to restore it from a snapshot. The key is containing the spread first. Investigation comes after the system is stable. Next scenario. Your daily backups are succeeding, but during a restore drill, you discover the restore process will take 8 hours. Leadership wants recovery in under 1 hour for a critical outage. No new hardware is available immediately. What is your judgment here? A strong answer could be: the gap between backup capability and recovery capability is a serious risk. My first step is to communicate clearly that the current setup does not meet the business objective. Then I look at optimizations. That might include using incremental backups, compressing less aggressively, or parallelizing the restore steps. I might also propose a warm standby instance that is continuously synchronized, which can be promoted quickly, even if full hardware upgrades are not possible yet. The judgment call is balancing what can be changed now versus what requires longer-term investment. Next scenario. Your primary database is healthy, but replication suddenly stops on all replicas at the same time. Logs are unclear and nothing obvious points to the root cause. You need replicas for read traffic and backup safety. What do? A composed answer would be, I treat this as a top priority reliability risk. First, I confirm replication threads, disk space, and network connectivity. If replicas have stopped consuming logs, I restart replication in a controlled way while watching for errors. If every replica fails immediately, that suggests a specific event in the logs is causing replication to fail. In that case, I isolate the offending log position and determine if it requires manual correction or rebuilding the replicas from a safe snapshot. During all of this, I shift read traffic to the primary only if safe, or temporarily shed non-critical reads. Stability first, optimization later. Next pressure question. You discover that backups contain sensitive customer data that should have been encrypted. These backups have been stored unencrypted for several weeks. No breach has been confirmed yet. What is your judgment call? A responsible answer would be, I escalate immediately to the security and compliance teams because this is both a technical and legal issue. Then I begin rotating and securely erasing the unencrypted backups. I verify that all future backups are encrypted at rest and in transit. I also review the entire backup pipeline to confirm where the breakdown occurred. The judgment call here is transparency and containment. Pretending the issue is small can have severe consequences. Addressing it directly is the safest and most ethical route. Final pressure scenario. You find that your primary database has started flushing write-ahead logs extremely slowly. Latency is rising, and you know from experience that a crash at this moment could cause irreversible data loss. You cannot immediately identify the cause. What do? A thoughtful answer would be, my priority is protecting data durability. I immediately reduce incoming write traffic to lower the load. Then I check disk health and IOPS to see if storage degradation is the cause. If possible, I move the WAL directory to faster temporary storage. I examine recent configuration changes or spikes in write amplification. If nothing obvious appears, I place the system in a degraded mode that limits risky operations until the root cause is found. A database on the edge of losing durability is too dangerous to operate at full speed. That brings us to the end of this interview session. These scenarios are designed to push your reasoning into areas where operational risk, data safety, and system stability collide. Working through them helps build the judgment needed to handle real-world incidents, where perfect information is rarely available and decisions have lasting consequences. Take a moment to think about which question challenged you the most. Was it the corruption spreading through replicas, the slow recovery time, or the dangerous delay in write-ahead log flushing? Each one reveals how important it is to stay calm, deliberate, and grounded in safety-first thinking. If you want to keep sharpening your skills with challenging real-world scenarios, make sure to subscribe so you do not miss the next interview.